I'm going to say the thing I say at every talk that I give that has LIGO results in it, which is if you take a picture of this, you can get to these slides, and every plot, slide, whatever, has Abbott et al. 2019, which is one of the 60 Abbott papers that LIGO published in 2019, but it's clickable. So you can find out which Abbott it is if you go to the slides and you click the link. Okay, because otherwise it's impossible to figure out which LIGO paper I'm talking about. And I will also apologize. Mark walked by and said how high frequency is high frequency. It's the boring high frequency. This is audio frequencies, not megahertz frequencies. That's a whole nother talk. I'm really talking about LIGO, right? LIGO and Virgo, ground-based interferometric gravitational wave observations. And maybe this is boring for this crowd, but I think it's kind of interesting to do a quick little run through why LIGO sees the sources that it does, and maybe the theorists' way to think about what LIGO can detect. Okay, so LIGO is an interferometer. It's got a laser. The laser goes through a beam splitter, travels down some arms, recombines, and is read out at a photodetector. Gravitational waves move freely swinging mirrors at the ends of the arms. Or if you don't like that gauge, the mirrors are freely falling and sit still, and they change the propagation of the laser as it moves down the arms, whatever you prefer to think about it, so that when a gravitational wave comes through, there's a differential between arm Y and arm X, and a little extra power or a little less power comes out of the photodiode. Okay? This colored plot here is grabbed from the paper about the very first gravitational wave detection that LIGO made, GW 150914. And it describes the fluctuations in the relative length, and actually the fractional relative length, the strain, delta L over L, in the instrument that was present in late 2015 when no gravitational waves are doing anything of note. Okay, so you can see that sort of at audio frequencies, like this is, my voice is somewhere here, right? At audio frequencies, the typical level of noise is 10 to the minus 23 delta L over L per root hertz. A 10 to the minus 23 fluctuation on a 4-kilometer long arm, you can do the math, it's really freaking tiny. Okay. LIGO detects the sources that it does because in order to make gravitational waves, you have to accelerate masses. You have to have a time variable quadrupole moment. The easiest way to do that is to take compact objects and put them in a binary orbit. Gravity does the acceleration for you. If you ask, what is the gravitational wave frequency that is emitted by two 10 solar mass black holes in their final stable circular orbit? It's 200 hertz. And it scales inversely with the mass because the Schwarzschild length scales with the mass, and they're moving at the speed of light. Okay? So LIGO is optimized to detect stellar mass objects doing, sort of their final cycles headed into merger. On the y-axis, this 10 to the minus 23 fractional strain, well, the strain is a dimensionless quantity. It happens to be the gravitational field, okay? H, this thing that actually propagates in Einstein's theory. Einstein's theory, for small perturbations, conserves energy. So H squared, just like E squared or B squared or any other field that can propagate through space, H squared has to fall off like 1 over R squared from the, as a function of the distance to the source, just by energy conservation. The area it's propagating into grows like R squared. The flux has to fall off like 1 over R squared, which means H has to go like 1 over R. That's also, by the way, true of electric and magnetic fields away from their sources. But H is a dimensionless quantity, so I need something with units of length to plop in this formula so that it can fall off like 1 over R. The thing that has units of length is the Schwarzschild radius. So if you imagine that close to the two black holes, the perturbation is order 1. As it moves outward, it simply shrinks by energy conservation. Then you will discover that the perturbation will be 10 to the minus 23 if the black holes are 10 solar masses and your distance is a gigaparsec. LIGO is designed to detect the gravitational waves from stellar mass objects that are close to merger over gigaparsec distances. You can just read that off this plot. Okay. And we have done so. So this is LIGO's first catalog, the Gravitational Wave Transient Catalog number 1. There are 10 sources here. This is a mass parameter. It's the chirp mass. Never mind. It's basically like the total mass times a small factor. And you can see that most of the sources that were detected were tens of solar masses. The luminosity distance of the sources was 1 to a few gigaparsecs, just as promised. Right? We're seeing stellar mass black holes a good fraction of the way across the universe. Right? This is, pushing out towards redshift 1 over here, so halfway to the Big Bang. Because LIGO actually, so this is the place, maybe this isn't the crowd, but this is the place where I have a little dig at the sort of traditional astronomers. LIGO actually measures the gravitational field. The snarky way to say it is no gravitons were harmed in the making of this measurement. Right? It's not a graviton bucket. A telescope, like an optical telescope, is a photon bucket. It just catches the photons. It measures energies or counts photon number. We measure field strengths. So if our detector improves by a factor of 2 in sensitivity, the limiting field goes down by a factor of 2, or the limiting distance goes up by a factor of 2. So every factor of 2 in sensitivity in LIGO is a factor of 2 cubed, 8, in volume. So we make the interferometer a little bit better, and we get our second catalog, which is about half the total observing time and comprised 4 times the number of sources. So the detector at 8 times the sensitive volume, observed for half the total time. We got about 40 sources. This is GWTC2. Again, these are tens of solar mass objects at distances of a handful of gigaparsecs. Also, in the sort of census of compact objects, we've gone from mostly seeing black holes. We've seen binary neutron star mergers now and black hole neutron star mergers. So these curves here, this is a pair of neutron stars, 2 things less than 3 solar masses. This is black holes paired with neutron stars. These are binary black holes. Most of what we see is this, because these signals are much louder and we can see them to redshift 1 or even greater. Most of what the universe merges is this. The actual merger rate, the astrophysical merger rate, is a few to maybe 10 times higher of these compared to those. The final public gravitational wave catalog is GWTC3. I don't know why there's a B there. I should get rid of that. Which is another 40 sources from the second half of our third observing run. So in total, we have about 80 mergers now. Those are mostly binary black holes, a handful of binary neutron stars, and some NSPHs. We are in the midst, literally today. It's the 5th. Sorry, literally yesterday. We are observing binary black holes, not with terribly high confidence, and announcing them to the world. So if you click that link there, it'll take you to the database GraceDB, where we post observations as fast as we can after they come in on a timescale of like minutes. And over the course of the last year or so, we have accumulated 199 additional candidates. We expect to release our 4th catalog in August. It will probably double the size of the extant catalog, so be another 80 to 100 black holes. Okay, so this field improves very rapidly because of that sensitivity cubed volume factor that I mentioned. There are plans in the works to build next generation instruments. Next generation, XG. For a long time, people were calling them 3G. But now 3G is a crappy cell phone signal, and so nobody wants to have a 3G detector. It's XG instead. Anyway, the next generation, which will be longer arms, enhancing the strain signal, fancier optics, et cetera, basically improve the sensitivity by a factor of 10, and will move the horizon redshift for, say, a 30-30 black hole merger out to redshift 100, which is beyond where 3030 black holes exist. Okay, maybe there's primordial black holes. This is the right crowd to say that. Who knows? But anyway, all of the stars are done making black holes long before redshift 100. So you will see all the black hole mergers in the universe. That's something like 250,000 mergers a year. This is an example. You can click there. There's a little GitHub link. You could make these plots for yourself. This is a Tuesday in the next generation era. 20 minutes of a Tuesday in the next generation era. And these are the sorts of signals you might expect to see. So time here, 0 to 20 minutes. Frequencies, again, in the 5 hertz to 100 hertz range. This little track of dots here is a binary neutron star that merged at redshift 1 point a few and has signal to noise that is louder than any signal we have released to date, 35. This little track here is another binary neutron star merger, merging at redshift 2 with a signal to noise ratio that would be very loud in our current catalogs, 20. And this huge scar there is a 1010 black hole at redshift 2.5, which has a signal to noise ratio of 150. So that if we get money and we build the next generation of detectors, this is what the future looks like. It's bright. Okay. There we go. That's everything you need to know about LIGO. Let's talk a little bit about cosmology. Another way that gravitational waves are different to electromagnetic observations is that for us, distances are actually easy to measure. Redshifts are hard for us. I'll come to that in a moment. But distances are easy. And the reason that distances are easy is this, c to the 5th over g, is a luminosity. It's a constant of nature. It's a large luminosity. It's 3 times 10^59 ergs per second, or 1,000,000 times a supernova luminosity, give or take, in order of magnitude. That is the luminosity in a binary black hole merger in its last cycle, independent of mass. The reason is the total energy emitted is some fraction of mc squared, so the energy gets bigger as the mass gets bigger, but the timescales over which it is emitted get longer as the mass gets bigger, so energy per time is constant. So we are standard candles, literally, right? At least if you believe GR. If you think GR is the wrong theory of gravity, it's not, but fine, then this could change. But if GR is correct, yeah, I see you're waving your finger around. Yeah, there's an inclination correction, and there's also an order 1 factor out here, which is actually like a few percent, not order 1. So the story is a little too simple, but basically we can solve all those problems. So we're standard candles. Redshifts for us, though, are quite hard. And the reason is, just like everything else, gravitational waves partake of cosmic expansion. So a gravitational wave that's emitted at some frequency f in its rest frame, as it propagates to us, becomes stretched, and its frequency appears at f over 1 plus z. Right? It moves to lower frequencies as it redshifts. But all that does for us is change the mass that we infer for that system. Right? We infer masses by examining orbital frequencies right before the plunge, or the rate at which the system is in-spiraling. So if the frequency is redshift, the mass is redshift. So if I don't know what mass I was supposed to have, I can't really say what redshift the signal occurred at. Okay, that's obviously a problem for cosmology. I want to measure distances and redshifts if I'd like to track cosmic expansion. So what am I to do? Well, playing the game on easy mode, you have some merger which also emits photons. The thing you're thinking of is GW170817, the binary neutron star merger that was followed by a kilonova that was detected in the X-ray, the optical, the UV, the radio, the infrared, across the electromagnetic spectrum. Then you do the easy thing with the electromagnetic measurements. You get a redshift of a host galaxy. And you do the hard thing with the gravitational waves. You measure distances, and you make the first gravitational wave Hubble diagram. Distance here, that binary neutron star merger, was at about 3540 megaparsecs. Redshift or recession velocity here, 3,000 kilometers a second. The slope of this line is the Hubble constant. Black holes are made of gravity. They don't emit photons, or at least it's hard to make them emit photons. But if you have them merging in the right places, There are ideas, which I will say are highly speculative, but ideas about how they could potentially emit photons. If you merge black holes, for example, in a supermassive black hole's accretion disk, an active galactic nucleus, then the recoiling remnant has enough energy that if it contributes that to the disk, it can cause a flare. If that flare escapes so that you can see it, you might see an AGN disk flare associated to a black hole merger. That may have happened for the most massive black hole merger we've seen, GW 1905-21. If it did, then you have a redshift from the AGN and a distance from the gravitational waves, and you infer a Hubble constant that is this huge broad thing here. If you combine that with the 1708-17 measurement, you get this blue curve here. As you can see, this is early days. We're talking about 20% uncertainty on the Hubble constant. These little bands here are the interesting bands relative to the Hubble tension, at least as of a few years ago. This is the sort of local distance ladder Cepheid measurement. This is the CMB measurement. They're very far apart. That's the Hubble tension. We can't say anything about that yet, but in principle, we could. However, you know, look at the dates here. It's 5 years on. Where are the counterparts? They're not coming in as fast as we'd like. We've got a lot of binary black holes, though. Is there something we could do with those? Yeah, there is. If somehow I could pick up the phone and talk to God, and she told me that the mass of the black hole that I just observed was 35, then I see this in my detector, I was told this, blam, I've got a redshift. I'm winning. Well, we don't have that phone, unfortunately. Sure would be cool. But what we do have is a black hole mass function that is not smooth and scale-free. So this was first pointed out actually fairly early on when we only had 10 sources. There's a great paper by Maya Fischbach. It's literally called Where Are LIGO's Big Black Holes? And that is the idea. LIGO should be able to see black holes up to hundreds of solar masses, given its frequency sensitivities. At that point, we had observed 10 black holes, and not a one of them was above 50 or 60 solar masses. Where are these guys? Okay. Already with 10 sources, you can tell there's a definite lack of those systems. Now that we have 80, those systems are very rare. Not zero. There's at least one system whose mass lives over in this regime, but 1 out of 80, it's rare. So following on that, I wrote a paper with Maya and Dan Holtz and my student, Johnny Yee, saying, well, golly, this is sort of like an absorption line in mass space. The black hole mass function goes up to 45 or 50, and then there's an absorption line. If you track that over cosmic time, making measurements of the things we actually measure, luminosity distance here on the x-axis, we're thinking about design sensitivity, our final targeted sensitivity, so this goes out to 15 gigaparsecs. And detector frame, that is redshifted masses, there's some kind of truncation in the mass function. It starts turning off here, it finally finishes turning off here, and you can see that you can track that edge. This is imperfect measurements. Here's with actual realistic error bars. We built this whole population model that fit the shape and the location of that edge. And if you do that, this curve here with these bands is basically the source frame mass times 1 plus z as a function of dl. So this is literally luminosity distance as a function of redshift, which means it can be used to constrain cosmological parameters. And in particular, if you use it to constrain the Hubble rate, you get the best measurement at about a redshift of 0.8. And there you can measure it to 3% if you can collect a few hundreds of these sources. We are going to collect a few hundreds of these sources. This is a measurement that we can make. Now, it turns out, when we had 10 black holes, we thought there was just a cutoff at high mass. Now that we have 80, we actually see structure. This is a paper that I wrote with Tom Callister a couple years ago, where we fit these very flexible models. Each of these little blue traces is one possible model for the black hole mass function. It's an insane model. It's allowed to jump around almost arbitrarily. But if you average them all together, you see a peak emerging at 10 solar masses and a peak emerging at 35 solar masses. Not very many black holes in this region that Maya was asking about, though not zero. Maybe there's something happening here. We don't really know. More sources will tell us. But the fact that there is a peak here, there's an excess of black holes there, that functions just like a spectral line. You can track it across cosmic time. Now, what happens, though, if this is the black hole mass function that we see now, because we can see to redshift, point few or maybe out to 1, but the black hole mass function at redshift 2 is different? Okay, that's the question you should be asking. If that's the case, you have a problem for a naive analysis. This 35 solar mass peak doesn't stay at 35 solar masses. Well, okay, I would love to reassure you by saying we know what causes the 35 solar mass peak. Our initial thoughts were probably not correct, but the initial thoughts, and we heard to talk about this yesterday, were that the 35 solar mass peak was due to something called the pair instability. Very massive stellar cores are hot enough that they pair produce. That softens their equation of state and leads to premature collapse and either explosive pulsations or complete disruption of that star, so it does not form a black hole, or it forms a lower mass black hole than it would have. That means that the initial mass to final mass relationship, which initially is growing, heavier initial masses make heavier black holes, turns over. And right here, where it is turning over, there's a finite range of initial masses that all map to 1 remnant mass. That produces a peak-like structure. The problem with this picture is that if you actually ask realistically in stellar cores, what mass would you expect to see this onset? What would be the remnant mass that results? It's more like 45, not 35 solar masses. And you can play with that a little bit by tuning nuclear reaction rates, which change the core size of these massive stars. But you have to push them 4 or 5 sigma away from lab measured rates in order to get this peak to move to 35 solar masses. So the answer is we don't really know what makes this peak. However, whatever makes this peak probably has some kind of structure like this. The initial mass function is thought to be a featureless power law. In order to get a peak out of a featureless power law, you have to go through some kind of map that has this kind of structure, right? There's got to be a softening in the initial final mass relationship to cause a pileup. What that means is that there is more information in the peak than just its location. If I want its location to move to higher masses, I have to pick up a higher mass piece of the IMF, which is declining. So the rate has to go down. If I want it to get taller, I have to make this range wider, which changes not just the height of the peak, but also the sharpness of onset and the sharpness of decay. If I want to make the peak very blurry, then I need a lot of scatter around this relationship, so I can build these sort of structural models. You might call them the gravitational wave Phillips relation, if you want to poke fun at type 1a supernova cosmology, which relate structural parameters of the peak to its location. And those are all things I can measure with gravitational waves. Now, currently, there's about 30 or so sources that might plausibly live in this region between 30 and 40 solar masses. We don't have a lot of traction about the shape of the peak. But we're about to double that number. And then in another year, when we release the second half of our 04 observations, we'll go up by another factor of 1.5. As we accumulate more and more and more black holes, we can check that the shape, the asymmetry, the height, right, all of those properties of the peak remain constant over cosmic time. That gives us some confidence that the process that produces the peak is calibrated and is putting it at the same location in the rest frame over cosmic time, and allows us to make this measurement. Okay, if you do this right now and pick out, these are the sort of 40 sources that are plausibly in the 35 solar mass peak. This is, again, this is their detector frame chirp mass. This is their distance. Here's one of these, distance versus redshift curves. It makes a 20% measurement of the Hubble constant, which is to say, not really useful. But this tightens up quickly as the number of sources increases. OK. Thinking towards the future, there's another peak here. There's a 10 solar mass peak. If you're worried that the 35 solar mass peak is moving around because of astrophysics, let me reassure you that the astrophysics in this peak is completely different to the astrophysics in that peak. So this one will also move around. But they won't move together. Redshifting moves them together. Astrophysics moves them around. So Jose Esquiaga and Dan Holtz wrote a really nice paper pointing this out and showing that by demanding only the homologous expansion, right, measuring only the homologous expansion of the peaks to do redshifts, in X, that should be XG, because nobody likes 3G, in next generation detectors, where you can see black holes to redshifts of 3, 4, 5, 6, then with a month of data, which comprises some few tens of thousands of black hole mergers, you can measure a cosmic expansion history out to redshift 2 and 3, which it beats, right? These are the error bars from DESI, full DESI. So the next generation of instruments can make this kind of measurement in a very, very interesting redshift range that is not really accessible or very accessible to electromagnetic observations. OK. I will say in the next generation of instruments, you can also do this with neutron stars. This is a great paper by Shumendra, who is over in the corner there, my graduate student, just pointing out that we don't expect the neutron star population to change much over redshift. Of course, that's just modeling at this point. We will learn when we observe them out to redshift 1. But if that is the case, then we can easily achieve percent level precision in the Hubble constant after, some tens of days of observing at, 1% precision in the Hubble constant after sort of tens of days of observing in next generation instruments. OK, that's a lot of cosmology. Now we're going to do a little whirlwind tour of other kinds of new physics things we can explore with gravitational waves. And the first, which is a sort of now become a standard part of LIGO analysis, is just to ask whether the actual structure of the signals that we see matches the GR expectation. So what I'm showing you here is an analysis of our LIGO catalog, GWTC3, so those 80 or so black hole mergers, where different post-Newtonian coefficients in the waveform models. So the post-Newtonian expansion is an expansion in powers of V over C, or curvature, or orbital radius, whatever you would prefer. These are all sort of the same thing. It's a power series expansion in that quantity that produces the evolution of the orbit and the gravitational wave signal as a function of masses and spins and the properties of the system. This plot shows what happens if you take the first term, the 0pn term in that expansion, and you deviate it with a fractional deviation of 10 or 20%. Our combined catalog is inconsistent. The signal morphology is inconsistent with deviations that are larger than sort of 5% in this 0pn parameter. And so on for the next and 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 the next parameter. We have much tighter constraints on the -1 pn parameter. This would be associated with dipole radiation, not quadrupolar radiation, and it's formally 0 in GR. It's also something that makes lots of modifications early in the orbit because it scales as a lower power of separation than the quadrupolar emission. So we would see whopping great evidence of that if it were present, and it's not at the sort of part per thousand level. Now, if you ask, what are the curvature scales or the length scales that are probed by our black holes? Our black holes are like 5, 10 kilometers across. We're not probing Planck scale physics here. If your natural expectation is the Planck scale is where GR breaks down, go to sleep. That is not accessible to us. It's not a thing that we can measure. But we should go and look, and we do, and everything so far is consistent with GR at the sort of percent or few percent level. Another thing we can do, which we've done a lot here, this is a paper by Max Isi, who's also in the audience, and this is the corresponding LIGO paper, is to look at the remnant black holes that are formed When the two black holes in a merger merge, they produce a remnant, which is in a very excited and perturbed state. And it will ring down, it will emit those perturbations in gravitational waves until it settles into a Kerr spacetime. That emission, at certain times anyway, is dominated by damped sinusoid quasi-normal modes. You're literally hearing the sound of the drum, right? The sort of shape of the space-time around the remnant. And by comparing what we measure for those mode frequencies to what you predict by doing perturbation theory on the Kerr space-time, you are effectively testing the sort of space-time geometry near the black hole, near the remnant. That was done for the first time here in 2019 by Max, and the result was that the perturbation on the frequency of one of the modes was 0 to within 20%. By stacking many, many, many observations on top of each other, now we think the perturbation in that mode is 0 to 5% or so. Again, if you think the Kerr metric gets modified at the Planck scale outside the horizon, this is irrelevant. But it's a test we can do, and we should. And it's exciting to hear the shape of black holes for the first time. We truly do live in the best of times. Another thing that we can do is we can look at the black holes in our catalog and see that they spin. They don't spin super rapidly. The dimensionless spin parameters are point few. However, if there were an ultralight pseudoscalar, like an axion, whose de Broglie wavelength was of order 10 kilometers, or whose mass was of order 10 to the minus 12 to 13 eV, then our spinning black holes would source that particle. They'd build up a huge cloud of those particles and spin down. So the fact that we observe black hole spins, this is the y-axis is the spin, x-axis is the mass, across a range of masses, places bounds on the existence of light pseudoscalar particles in this range of masses. Again, that's maybe not the best place to be looking for the QCD axion or any other expected light pseudoscalars, but we can do it, so we should. So we do. Okay. A final fun thing that we can do is we can use our gravitational waves just to probe space-time between the emission and our detector. We can do propagation tests. This isn't something that's specific to gravity, but we now have these waves propagating, and we can measure their properties. We should look at them. So something we did in this group was to ask, suppose that GR was not the right theory of cosmology. Instead, there was something like dynamical Chern-Simons gravity, for example, or any other theory, really, which has some kind of parity violating or parity odd particle in it that interacts with gravitational waves. If that situation obtains, then the left-handed gravitational wave polarization can be suppressed exponentially, and the right-handed gravitational wave polarization enhanced, or vice versa, depending on the gradient of this scalar. We would expect to see birefringence, different propagation of left and right polarized gravitational waves. We can look at our catalog of gravitational waves, and we can ask whether we see equal amounts of left and right as a function of distance, and thereby place constraints on the birefringence of space-time. And the answer that we get is that there is a birefringent attenuation that is less than 5% per gigaparsec. So if you set up your dynamical Chern-Simons cosmology, you'd better not make your scalar have too large a gradient. Okay, that's the answer here. This is about the best constraint going for these types of theories. LISA, a future space-based mission, will see gravitational waves at higher signal-to-noise ratios over the same kind of distance, but much longer wavelengths. And the attenuation is per cycle. It's exponential. So we win by having way more cycles of oscillation between source and detector. So as the catalog builds up, this will get better and better and better, but not orders of magnitude. Another question that we can ask, which is actually another place where we dominate electromagnetic astronomy, is we make measurements of the orientation of our source by measuring gravitational wave polarizations. So we can ask, do all of our black holes point to a special place in space-time? I don't know why they would, but there are theories, right, where you have spontaneous symmetry breaking. There's some vector field that condenses out of the ether and gives you a preferred direction. Maybe your black holes respond to that. Okay? And we can place limits on this. When we do that, this is a beautiful visualization, actually, that Max worked up. This is where the angular momentum vector of all of our black hole mergers was pointing on the cosmological sky. For some sources, we have really no idea where it was pointing. For other sources, we know rather well where it was pointing. You can stack all of these together into a heat map, basically, and ask, is there a preferred direction for the orientations of these black hole orbits? And the answer is no. There is a hot spot, but it is consistent with statistical fluctuations. It's perfectly consistent. Our black holes are oriented isotropically. Newsflash, I'm sure you're shocked. You also can ask, and in other papers people have asked, this is one, whether the black holes are coming uniformly on the sky. So that's not isotropy in where they're pointing. That's isotropy in where you are pointing to see them. And the answer there is yes, also they are fully consistent with isotropy. Again, no surprises. It's a good thing to check. We can continue to improve these sorts of constraints as our catalog grows. And I'm going to stop there, and you can ask me questions. Thanks, everybody.
Great, thank you very much, Will. Questions? Hi. Is there a known origin for the 1010?
In the same sense that there isn't really a known origin for the 35 solar mass peak, there is not really a known origin for the 10 solar mass peak. There are a number of theories about how you might get it, including one 2 rows back by Lika, which is a personal favorite of mine, which has to do with the stability of mass transfer at these masses, removing the lower mass systems. But no, there's no definitive evidence one way or the other.
I wanted to ask, could it possibly be a selection effect? You were saying this is precisely
Yeah. It really, I think, cannot unless we have made some horrible, horrible mistake. These plots are selection corrected. And for us, that's pretty straightforward to do because we can generate oodles of these sorts of waveforms and put them into real detector data and run them through the same detection pipelines, and so estimate our completeness to essentially arbitrary accuracy. So no, the fact that this goes down at low masses is not just these are harder to detect. That's all been removed. And it really does go down from the peak at 10 solar masses. But that is a good question to be asking.
Another question about Simon's theory, if that's okay.
Yeah.
Imagine they require some kind of model for what the scale is doing with the cosmology.
Uh-huh.
So is there some kind of model or initial condition of your bounds? Or?
Our bounds are not expressed in terms of the amplitude of the scalar or the length scale of its coupling or anything. They are merely the attenuation is less than 5% per gigaparsec. If you want to turn that into a bound on parameters of the DCS theory, then yes, you have to make up something that the field is doing or make up a kinetic term that makes it do something on its own, and then turn those coefficients into attenuations and ask what's happening.
Oh, sorry. There's a microphone here, I think. Okay.
Sweet.
You'll presumably be measuring the gravitational waves so frequently that you might actually get a few that might interfere with each other. Is that something you guys are thinking about at all?
So many of them interfere with each other. Yeah, Mark has been on papers about this. What's not shown here, right, is sort of, you can see from this plot, this is not actually done with real Poisson rates, but it's not too far off the actual merger rate that you'd expect. So sort of above 10 hertz or so, these tracks don't overlap. Most of these time frequency pixels are empty. If you want to look for stochastic backgrounds, for example, you can use all these places where the gravitational waves aren't. Below 10 hertz, the signals live much longer, And in fact, this signal overlaps with that signal in the sense that they are both at the same frequency in the detector at some past time when it was sensitive. So yeah, below 10 hertz, you start running into this sort of signal overlap problem, and you have to do something more clever. And of course, that depends on the rate of neutron star mergers at redshift 2, which we don't know. So the 10 hertz number is an order of magnitude guess, but it may be lower or higher depending on the actual merger rate. But that's 100% a worry, and people put a lot of energy into it.
About the peak at 35. Okay, there's been models like the Farr et al. And some combination of binary evolution and choosing where essentially where the parent stability comes down seems to shift that thing down to 35. We didn't go out looking, trying to.
Yep.
We just we used the Salem code and it just came out of the box.
Nice.
But the problem was getting enough black holes of that, to actually
Yeah.
explain the amplitude.
Yeah.
The peak did come out closer to 35 with the binary evolution.
That's fantastic. I will say I love it. More of this should be done. To my knowledge, you're in the same situation as everyone is, which is there's always something, the location, the height, the width, the relative rate at 20 to 30, yeah, no one can just make it perfectly.
I mean, part of the thing is you don't know the IMF at those high mass ends.
Yeah.
We're talking about 60, 70, 80 solar mass.
Yeah, that's right.
And so presumably that's saying something about the IMF itself in these.
Maybe. Yeah, that's right. There's some measurements in 30 Doradus that go to 50 at least and suggest the IMF still is power law-ish, but maybe a shallower power law than the saltpeter law. But you're right. Yeah, and that's not at the right metallicity for most of the systems that probably make our 35 solar mass peaks. So it's, yeah, things are very uncertain. There's beautiful astrophysics here, I'm sure you know. Since this is more of a cosmology crowd, I'll say from the cosmological perspective, I would not hold my breath at predicting this from first principles, and I'd instead, it's the Phillips relation. You calibrate it. You measure shapes and widths and heights and, build confidence that way.
Any more questions? All right.
Maybe just marginally in next generation detectors. What you'd really be detecting, there's a slight relativistic boost, beaming basically, energy difference from along versus perpendicular to the direction of motion, but that's gamma squared, so it's quite weak. And it would manifest as sources that are along your direction of motion seem to be a little bit closer to you if you don't account for the beaming. They're just a little brighter. But, at the 10 to the minus 3 level. So to detect that is very hard. There's also an aberration effect from the fact that the sky gets compressed. That also is very small, and you need a huge number of sources in order to see it. Because we don't measure redshifts with spectroscopic precision, we don't really see the Doppler. So it's not the same kind of dipole that you're probably thinking of.